Hi everyone. So welcome to lecture number 6 of counting. So we are doing data science and AI complete gate course, and we are discussing counting. And this is lecture number 6, and we will continue discussing combination with repetition. We started it in the last class, and we said that whenever we have n objects and we have to pick r at a time, and repetition is allowed, then it comes under the category of combination with repetition. Always remember, combination is selection, so arrangement is not important, just the selection is. So always map it to like cricket example or something, like have a mapping, okay? So, and if arrangement is there, we will see it later. It is permutation with repetition, okay? We will see that as well. So, but permutation is repetition with repetition will be very simple problem. We will solve it like in this lecture only. The more difficult problem to solve is combination with repetition, because always counting the number of selections is slightly difficult, because there we tend to overcount. Whenever arrangement is important, that problem can be solved like by making r spaces, and we will have options to choose, okay? That is easier to solve, I will tell you in this lecture, okay? But combination or selection problem is slightly trickier, and that's why like I emphasize more on combination with repetition or selections, okay? Cool. So let's continue. We have already seen that the number of combinations of n objects taken r at a time, that this problem will be difficult. Always map it to an equation. So you have n objects taken r at a time, so you take x1 of first object, x2 of second object, x2 of second object, and so on up to xn of nth object, and total number of objects you have to take is r. So number of non-integral solutions to non-negative integral solutions to this equation is equal to you draw n plus r minus 1 boxes, and you insert n minus 1 sticks, so you will get n separations, and total number of boxes left will be r. So this is the number of solutions to this equation, okay? And this is also equal to n plus r minus 1 choose r. We know that by k selection is equal to k rejections, and this formula comes out to be this. We have seen this. So now let's solve some examples. So the first example is, in how many ways can 100 identical candies be distributed among 7 children, okay? So this is a different way of forming that equation, okay? So always combination with repetition might not be as it looks. So the standard way to write is like n objects and take r at a time with repetition allowed. But the problem can be formulated in a different way like this. So that's why I told you not to remember formula. Always map it to equation. So you have to distribute 100 identical candies. So let's say this is a candy box, and it has 100 candies, exactly 100 candies, and they are all same, identical candies, and you have to distribute among 7 children. Now 7 children are different here. This is the first child, second, and you have 7 children, and you have to distribute these 100 identical candies to this. So you might be unfair. Some child might be like you don't want to give any candies to them. That is okay. No condition is mentioned. So you can assume that some of the children might get 0 candies also. So it's the standard problem. So let's say first child gets C1 candies, C2 candies, and so on. The 7th child gets 7 candies. So you have to distribute total 100 candies, right? So you just have to find the number of solutions to this equation, where all C1, C2 and C1 up to Cn can be greater than or equal to 0. So we already know how to do this. Don't remember the formula. How do you do that? If you have to make 7 partitions, you have to insert 6 sticks. So you have to create 106 boxes, and you have to insert 6 sticks like in them, so that you will have 7 partitions. So the number of solutions to this equation is 106 C6. You can go with the formula as well. N is equal to 7, r is equal to 100, n plus r minus 1 choose n minus 1. So there are 106 C6 ways. It will be a large number. I am not calculating it, but this is the answer, okay? So now let's move to the next problem. In how many ways can we fill a bucket with 100 balls of 7 colors? Again, a really different way to solve it, okay? Like form the problem. Previously it was 100 identical candies, right? 100 identical candies and 7 different children. Here it is 100, here there are 100 balls, okay? So you have to fill a bucket. There is only one bucket. This is your bucket. And you have to fill it with 100 balls of 7 different colors. and here you can assume that all balls of one particular color are same, right? So you have ball with 7 colors, and here also nothing is mentioned, so you can assume there is an infinite supply of all the balls. Nothing is mentioned, so you will assume, right? You will assume that you have 100 balls of red color or any color, you have infinite supply. So basically there are 7 colors, let's say a red, green and so on, okay? So let's say Vibgyor, anything, right? Let's say there are 7 colors, violet, indigo, blue, green, yellow, orange and red. And you have to fill a bucket with 100 balls of these colors. So you will have a few white balls, you will have a few yellow balls, you will have like balls with different colors, okay? Okay, so you can have red balls or blue balls or green balls. You will have 100 balls but of different colors, okay, in this. So basically what you want to do, you can have all 100 violet balls, you can have all 100 red balls also, and you can have some combinations, like you can have 20 violet balls plus 20 indigo balls and so on, like 5 red balls. But their sum should be equal to 100 because you have to fill 100 balls in this bucket. So what is it? So let's say you have x1 balls of the first color, x2 balls of the second color, and so on. You have x7 balls of the 7th color. You have x7 balls of the 7th color, and total number of balls you want is 100. Always map it to equation, it will be very simple, okay? And you have to solve this equation, and you might pick 0 balls of any color, right? So again you have to solve the problem. Like in the last problem we also had the same equation, so the number of ways in which you can do it is 106 C6, okay? Or you can apply the formula as well. So this is what you will get. Okay, let's move to the next example. This is a problem which I gave you as a homework, right, in the last lecture. In how many ways can 50 be represented as a sum of 3 natural numbers? We already solved it for 3 whole numbers. Whole number are greater than or equal to 0. That was simpler. So there the equation was x1 plus x2 plus x3 is equal to 50. And x1, x2, x3 were all 3 were greater than or equal to 0. This was the equation which we already solved, and the answer would be 52C2. But now the problem is slightly different. So you have to represent 50 as the sum of 3 natural numbers, okay? So here the equation changes a little bit, okay? So here the equation is this, but since natural numbers are greater than or equal to 1, so x1 has to be greater than or equal to 1, x2 has to be greater than or equal to 1, and x3 has to be greater than or equal to 1. Okay, so try to solve it. I'll give you the solution now. So whenever question like this comes, try to map it to whole number problem. Try to map it to whole number problem. How? x1 can be greater than or equal to 1, right? So there is a standard trick to do it. I want to map it to a problem to a different space. I want to map it to a different space in which the variables are greater than or equal to 0, not greater than or equal to 1, because that I can solve. So why not write x1 as 1 plus a? I am writing x1 as 1 plus a. Basically what I am trying to do is, since x1 has to be greater than or equal to 1, I am giving one, like I am making sure that x1 will be at least 1. So I will basically write x1 as 1 plus a, and I will write x2 as 1 plus b, and I will write x3 as 1 plus c. Why? This way I am ensuring that x1 is at least 1. Now a can be greater than or equal to 0. So if a is 7, x1 will become 8. If a is 0, x1 will become 1. Right? So this way I am making sure that x1 is at least 1, x2 is at least 1, and x3 is at least 1. So basically I am writing x1 as 1 plus a, x2 as 1 plus b, and x3 as 1 plus c. This will work with any value. If x3 had been greater than or equal to 5, I will write x3 as 5 plus c. So what will this equation become? So write it this way, this equation will become 3 plus a plus b plus c. 1, 1, 1 is 3, a plus b plus c is equal to 50. And now consider this. So now this is magical, right? Now since x1 is greater than or equal to 1, and I am writing x1 as 1 plus a, so it becomes 1 plus a greater than or equal to 1. So it means a has to be greater than or equal to 0. This is what I wanted. So this equation is equivalent to this equation. A, b and c have to be greater than or equal to 0. Right? and this equation I already know how to solve. Basically I am giving 1 1 1 to x1 x2 x3 already. So now 50 becomes 47 only, right? So this equation is nothing but a plus b plus c is equal to 47. And now ABC can be anything greater than or equal to 0. So this how to solve 47 and like 2 partitions, so 49 C2. If you create 49 boxes, insert 2 sticks, you will get like all the different ways in which you can solve this problem, okay? So there are 49 C2 ways in which 50 can be represented as a sum of 3 natural numbers. How to solve it? Always combination. So like always go with permutation first, 49 into 48 upon 2. This is 49 C2. It will be 1176, you can check, okay? So coming to the next problem. So right now in these problems we assumed that we had an infinite supply of objects. When I said that you have n objects and you take r at a time, I assumed that I have infinite supply of all the objects. Infinite means like I don't want infinite, I need at max r. I will not take r plus 1 anyway, but I was assuming basically that I have what I will need. So when I said that I need the number of solutions to this equation x1 plus x2 plus x3 is equal to, let's say, 10, right? I assume that x1 I have enough supply of x1. I have at least 10 x1s. I will not need more than 10, but that's what infinite means here, right? So sometimes it is possible that you are not given an infinite supply of x1, x2, x3. It is restricted. So the only equation right now, the condition was x1 has to be greater than or equal to 0, right? What if they add one more condition, ki x1 should be less than or equal to 5, right? x1 cannot go beyond 5. You don't have an infinite supply. Instead, you have a limited supply. You only have 5 x1s and so on. So that is a slightly trickier problem. And the most complicated versions of these problems can be solved only using inclusion and exclusion. So we will need both combination of repetition and inclusion and exclusion. So we will see inclusion and exclusion in the later part of this course in the same playlist. But for now, this problem can be solved without inclusion and exclusion. That's why I added it here, okay? More complicated variations we will solve later. So right now this problem, let's see. A girl has choose 4 items from a bucket which contains 3 red, 3 green and 4 blue balls. It contained 3 red, 3 green and 4 blue balls. Okay? And we have to pick 4 items out of it, 4 balls out of it. Right? So had it been we had an infinite supply, this problem would have been simpler. Let's say you are taking R red balls and G green balls and B blue balls. So you have to take 4 balls total and we have an infinite supply. You just have to solve this problem where R, G, B can be greater than or equal to 0. So then the number of solutions would have been 6C2. Right? But now this is not the problem. So here the here there is a constraint. The constraint is you only have 3 red balls, you only have 3 green balls and you have 4 blue balls. So basically here R can be anything between 0 and 3. R can be anything between 0 and 3. G can be anything between 0 and 3. B can be anything between 0 and 4. This is the constraint that we are adding. Okay? We are not having an infinite supply, we are having a limitation on total number of objects that we have. See, let's solve this problem first, assuming that we have an infinite supply. We know that there are 6C2 possible solutions to this equation, right? N plus R minus 1, choose N minus 1. So 6C2 becomes 6 into 5 upon 2, which is 15. There are 15 solutions, different solutions to this equation. But we cannot, so like we have to eliminate all those choices which are exploiting these conditions, right? There are only 2 cases in which this condition is not satisfied. Think about it. Since, see, blue balls we already have 4. We don't care, like we will not need more than 4 balls anyway, right? So like if the solution is like 0, 0, 4, 4 red, 4 green and 4 blue, it is allowed because we have 4 blue balls. But this solution is not allowed, 4, 0, 0. Why? Because we don't have 4 red balls, we only have 3 red balls. 4 red balls is not allowed and this solution will be a part of these 15 solutions. So there are only 2 solutions which are prohibited. What are those? In which we are taking all 4 red balls and in which we are taking all 4 green balls. These 2 solutions are not allowed. Otherwise everything is allowed if you see the conditions, right? More complex problems, see here it was easier. There were only 2 options to be eliminated. Sometimes it will be very large. So that we will solve using inclusion exclusion, that's a different principle. But for now, among these 15 choices, only 2 are prohibited. So we will remove those. So we have 13 possible ways or 13 possible solutions to this question, okay? I hope you got it, okay? Also write in the comment section if you have problems in any of these questions. I will read them and answer them in the comment section itself. And also I will be having live doubt solving and problem solving sessions, you can ask them there. Cool. So this was all about combination with repetition. So we are selecting objects, R objects out of N objects where repetition was allowed. Only selection, the order was not important. In which order I am taking, that was not important. The only thing important was how many x1 items I am taking, how many x2 and so on, right? But now we can have permutation with repetition as well. Okay, what is permutation with repetition? Again, we have N objects, we are taking R at a time, but order is important. Order is important, and now the problems become much easier, you will see, okay? So what happens is, you have N different type of objects. You have object 1, object 2, object 3. You have N different type of objects, and you have N choices each time. So basically what we want to do is, we have R places to fill. We have R places to fill, and the order is important. So basically you can take any object for the first place. You can have, let's say, the 7th object here. You can have again the 7th object here. You can have the nth object here. You can have the first object here. You can have the second object here. So for every place you have n options. Fill the first place and fill the second place, you have n options, and fill the third place, you have n options. Rule of product and. So it will become n to the power r. See, this was a very simpler problem because here the order was important. So basically, if you have, so like we saw a problem, right, in the previous lecture. You have A, B, C, D, and you have to fill 3 places. In the previous lecture we saw it was combination with repetition. How many selections of 3 objects are possible from A, B, C, D? Only selection. So here A, B and A, B, A were same, I told you, because both are 2 A's and 1 B. But in permutation these 2 are different. So it becomes a very easier problem, because how do you solve it? You just take 3 options, like three places, and for every such place you have 4 different options: A, B, C, D, A, B, C, D and A, B, C, D. Take any one of them, it will be different permutation. So it will be 4 cube. So permutation with repetition is like very simpler problem. If you have n objects and you have to fill r places, you have n options for everyone, so n to the power r. So it becomes n to the power r. Okay? In combination it was n plus r minus 1, choose n minus 1. Cool. So I hope you got it. In the next lecture we will solve a few problems on permutation, basically whatever we have discussed: permutations, combinations, factorial, with repetition, without repetition, everything. Okay, so we will solve a few problems so that it will be more clear. Cool, thank you, bye bye.